Hi everybody, it's Ben from Hike Club here, and today's daily lesson is going to be about forces in climbing. So forces in climbing is one of those things that I think people often don't understand well enough, but also tend to overcomplicate. They think it's hard. It does involve a little bit of math, and we'll talk about the math, but the math is pretty simple. And most importantly, this will tell you a lot more about the equipment that you're using in climbing and what that means. So for example, if you've ever looked at one of your carabiners, on your carabiner, there's the most poorly drawn carabiner in the world, and there's the gate. There you go. On the carabiner, on the side, they'll always have a bunch of little numbers written up over here, and it will look something like this. So you'll have two arrows pointing in the direction, and it'll say 24 KN, and it'll have something like this, and it'll say 8 KN, and it will have something that looks like this, which means open carabiner, and it'll say something like 6 KN. And so the same thing is true if you ever look at, say, your ropes or your slings. A sling might have a strength of 22 kilonewtons, a rope might have a strength of 30 kilonewtons. And the thing is, I don't think a lot of climbers understand what this information actually means. So today we're going to talk a little bit about it. We're going to talk a little bit about the physics of all of it, so you can get a better understanding of maybe how close to the danger zone for the equipment that we use, how close we actually operate to that. So let's begin with an easy scenario. We're going to take a person who's dangling from an anchor. So here we have an anchor, and we've got our rope, and we've got our climber just dangling from the anchor. So they're not climbing, they're not doing anything, and the first thing that we want to talk about is what is the force on this system. So what's the force here? So force is a measurement, and there's a formula to figure out. So force equals your mass, so basically how much you weigh, times acceleration. Now, in this case, you might be thinking, wait a minute, we just said this guy is stopped. How can he be accelerating? Well, the reality is, even while he's stopped, he's still being pulled down by gravity. So in our climbing scenarios, gravity is always our force of acceleration, because the reason that he stopped is because the anchor is providing a force to oppose that acceleration of gravity. For the purposes of this lesson, we're going to use some nice round numbers, so things that I can do math in my head. Overall, in reality, the acceleration of gravity is equal to 9.82 meters per second squared. We're going to round that off. We're going to call it 10. 10 is a good, easy number for us to use in our head. And also, our mass has to be in kilograms here, because it's all metric. And please don't ask me to do this in imperial. Our mass, I'm going to use 100 kilograms. So 100 kilograms is equal to about 220 pounds. And I'm aware that, very, very few climbers actually weigh 220 pounds. However, it's at least, again, an easy number that we can do some math in our head, so it's a good example to start with. And so if you weigh 75 kilograms, you can just take the numbers that we're getting, and you would be 3/4 of that. So we'll start with our climber dangling from the anchor here. So this is pretty easy to figure out. So our force is our mass times our acceleration. I just gave these numbers. Our mass is 100 kilograms. Our acceleration is 10 meters per second squared, which gives us 1,000 kilogram meters per second squared, which gives us, so this idea of a kilogram per meter second squared, that's just a measure of force. There's a much easier way to do that, and that's called a Newton. So you might remember this from earlier. Now we have 1,000 newtons. A newton is just 1 kilogram per meter per second squared. So 1,000 newtons or 1 kilonewton. So 1,000 newtons is the same as 1 kilonewton, just like 1 kilogram is the same thing as 1,000 grams. So in this case, the force on an anchor that we build, the force on the climber, is 1 kilonewton. So remember earlier we were talking about it, maybe the rope has a strength of 30 kilonewtons. A carabiner will be somewhere usually between, say, 22 and 26, so let's call it 22 kilonewtons. Our rock climber, he's got a braking strength of about 15 kilonewtons for our climber. So overall, in the system, we're not anywhere near approaching the fail strength of any of the equipment between our climber, our rope, or our anchor. You'll notice the climber is the weak point in this. So this would be a good scenario, for example, when you're rappelling, maybe when you're caving, so something where you're just dangling off of a rope, off of an anchor. However, for us in climbing, it's usually a little bit different. Because when we're climbing, we don't often actually just dangle from a rope off of an anchor. We will often have a belayer. So if we add in our belayer who's belaying and our climber who's climbing, what we know is that this belayer is being pulled down with 1 kilonewton of force. We just did that math. But what that means is that he's no longer dangling from the anchor, he's actually being counterbalanced by the belayer on the other side. So this person has to act as a counterbalance to this guy or girl. And so that means that this person is also being pulled down with 1 kilonewton of force. And what that means is that here on the anchor, it's actually resisting both this and this. So here on the anchor, we have 2 kilonewtons of force. So we just doubled the force on our anchor. And again, we're a long ways off. We've got, we're only about 10% of the total strength in a system where we're just dangling from our ropes. But all of a sudden you can see that, adding in a belayer doubles the amount of force that we end up having on our anchor. So this is a pretty common scenario. This is what's called a static system, so a system where nobody is moving. However, again, in climbing, we're often moving. So what we want to do is we actually want to calculate what does this look like when somebody is, and I'll start with, again, an easy example, when somebody is top roping. So if we go back to, again, a similar system, this goes up through an anchor, and then down to a belayer. Now what we're going to have is this person is going to climb up a little bit, and then they're going to fall. And the nice thing about a top roping system is that our fall distances aren't usually very long. Maybe you'll fall a foot or so because that's whatever slack you have in the system, and then the rope will catch, and then the rope will stretch, and then you'll come to a stop. So there's actually a different force formula for a system where things are moving. So in a system where things are moving, our force formula is force equals 2 times the distance that you fall plus the distance the rope stretches all divided by the distance that the rope stretches. So basically it's the total distance you fall plus the distance that the rope stretches, added together, times 2, all divided by the distance that the rope stretches. So let's give this a quick example. Well, actually, let's talk a little bit about this question, this distance of rope stretch, before we start talking about actually plugging it into this formula. So in climbing, you can imagine that it's a good thing that the ropes that we use stretch. What that means is that as you're slowing down, the rope goes just like a spring. And this is what we want. The longer that stretch period is, the slower or the less force that we actually have. So the analogy would be you would rather drive your car into a puddle of Jell-O than you would into a brick wall, because the brick wall has no give to it, where the Jell-O goes, and you might have some time. So the ropes that we use in climbing are stretchy. They're what are called dynamic ropes. And all dynamic ropes have different stretch characteristics. Typically, thinner ropes, so thin ropes stretch a lot. And thicker ropes stretch less. Typically, a thin rope will stretch somewhere around about 40% in total, and a thicker rope might stretch closer to 30%. In climbing, or in the climbing world, there are some other kinds of ropes. At a climbing gym, you might use what's called a semi-static rope. And semi-static ropes tend to stretch about 12%. And in things like abseiling and canyoneering, you might have what's called a static rope. And static ropes stretch very little. They stretch about 1% and sometimes less. So if we say that for our climbing purposes, we want for at least for the minimizing the forces purposes, we want to reduce our stretch, or reduce our force as little as possible. That means that we want a stretchy rope. So we're gonna, again, just use some good easy numbers. So we're gonna say that our rope stretches 33%, because I can do the math with 1/3 in my head. And so let's go back to our formula here with our little guy who's top roping. Our formula was that our force is equal to 2 times the distance that you fall plus the distance that the rope stretches, all divided by the distance that the rope stretches. So in a top rope scenario, let's just pick a number. So let's say that we've got a top rope, because we need to know the length of our rope, set up, and the distance from the ground to the anchor is, let's say, 15 meters. It's about 50 feet. And the distance that our little climber dude is from the top, let's say that that number is 5 meters. So that gives us a total rope length of 20 meters. So let's say that he's climbing up, and our belayer's doing an okay job, but not perfect. So let's say that his fall, he's climbing up, and he falls 1 meter before the rope goes tight. So that's 3 feet. That's a little bit of it's a top rope whipper, but it's just a top rope fall. So that's not too big a deal. So if we plug it into this formula, which we'll do right here, our force is equal to 2 times the distance that we fall, which is 1 meter, plus the distance that the rope stretches. So we said that we have a total of 20 meters of rope stretch, and we said that our rope will stretch about 1/3 of its length. So 1/3 of 20 meters is about 6, let's see, it would be about 6 2/3. So let's call it close enough to 7. And then all of this divided by, again, the distance that the rope stretches. So that's going to be 7 again. So here, we'll just do the math. This is 1 plus 7 is 8, times 2 is 16. So that's equal to 16 divided by 7. And that's equal to 2 and a bit. Let's call it 2/7 is, let's call it 2.3. So we'll call it approximately 2.3 kilonewtons. Now remember, this 2.3 kilonewtons is the amount of force that the climber feels. The belayer has to counterbalance that as well. So our belayer also sees 2.3 kilonewtons of force. And that means that our anchor, up over here, is going to see approximately 4.6 kilonewtons of force on the anchor. So now we're starting to creep up. But again, we are still way, way, way under the limit of things happening. So that's what happens, or that's what it looks like here in a top rope scenario. What we want to do now, maybe let's shift to something a little bit more challenging. Let's shift to a lead climbing scenario. Ooh, this is getting pretty exciting. Okay, so in a lead climbing scenario, the picture looks a little bit different. So here is our belayer, and here's a bolt, and here's a bolt, and here's a bolt, and here's our climber. And so in this scenario, let's put our rope out here. Let's do this. We'll do this a little bit more vertically to make the math a little bit easier. There's a rope going up the side of the cliff. There's a bolt there. There's a bolt there. There's a bolt there. Okay. So in this scenario, let's do the same thing. So let's say that our climber here is 3 meters. It's pretty run out, but let's say it's 3 meters above the last bolt. And then the ground to the most recent bolt here, let's say that that is 9 meters. Now let's say it's 15 meters. So it's 15 meters from the ground to the most recent bolt, and then 3 meters from the most recent bolt to where our climber is when he falls off the wall. So let's go back to our formula here. So pretty simple. Force equals 2 times the distance that we fall. So if we are 3 meters above the bolt here, what that means is that our climber is going to fall first 3 meters down to the bolt, and then they're going to fall another 3 meters down below the bolt before that rope gets tight. So our fall distance in a lead climbing scenario is twice the distance that you were above the last bolt. So in this case, it's 6 meters is our fall distance, plus the distance that the rope stretches. So in this case, our rope is we've got a total of 18 meters of rope out. 15 meters from the ground to the bolt, and then another 3 to the top. So a total of 18 meters of rope out, and then it's going to stretch by about a third of its length, so that's going to be another 6 meters. And then we're going to divide that whole thing by just the distance that the rope stretches. So there's, again, another 6 meters, and we're going to punch all of this in. And what we get is 12 times 2 is 24. Divided by 6, which gives us 4 kilonewtons of force on the climber. Again, also 4 kilonewtons of force on the belayer, which means that here on the bolt that we've just fallen on, we've got 8 kilonewtons of force. So again, we're creeping up there, but we're still, at about a third of the total strength of everything in this system. So pretty good so far. So now you're going to think to yourself, okay, what if we have a really bad climbing fall? So let's take a scenario where I've got, let's say the same climber, same belayer, same wall here. There's just one bolt clip there in the middle. And let's say that this distance here is 9 meters, and our climber is now 9 meters above his bolt. Let's assume that they're hanging in space, so he's not going to land on the ground, because that's a strong possibility here. So our force is going to be equal to 2 times the distance that he falls. So in this case, our distance of fall is going to be 18 meters plus the distance that the rope stretches. So I've got 18 meters of rope out, and so a third of that is going to be 6 divided by, again, the distance that the rope stretches, which is 6 meters. So we do the math on this. 18 plus 6 is 24, times 2 is 48, divided by 6 is 7. Nope. Is 8, sorry. 8 kilonewtons of force, and that's 8 kilonewtons of force onto our climber, 8 kilonewtons of force onto our belayer, and here in the middle, it's 16 kilonewtons of force onto our bolt. Now we're starting to look at some pretty interesting numbers, because at least in theory, that bolt is strength rated to 22 kilonewtons. So we're getting awfully close to the strength rating of that bolt. What if we have, we'll go one more scenario here. The worst kind of fall that you can have, and that's a fall where you fall right on to the anchor. So you've been climbing up and you don't put any protection in at all. You never clip a bolt or you never place a piece of pro, and you fall right down on your anchor and right past your anchor. So again, let's use some numbers here. So let's say that we are, let's go with 3 meters above the anchor. I can't imagine you would climb a whole lot further than 3 meters before you would want to, before you'd be able to clip the first bolt or place your first piece. So let's use that as a number. He's 3 meters above his anchor, and again, he's dangling in space, so he's not going to hit the ground. So let's plug this in. Our force is equal to 2 times the distance that he falls. So here, he's 3 meters above the anchor, so he's going to fall another 3 meters below that. So that's 6 meters times the distance that the rope stretches. So in this case, I've only got 3 meters of rope out. So 3 meters of rope, cut that by a third, or cut that down to a third of that number to get our distance of our rope stretch, which is 1, divided by, again, the distance that our rope stretches is 1 meter, which is 7 times 2, which is 14, divided by 1, which is 14 kilonewtons of force onto our climber, 14 kilonewtons of force onto our belayer. And what that means is that here at the anchor, we're going to see twice that, because it's got to support both the belayer and the climber. And we've got 28 kilonewtons of force here at the anchor. Now, you'll notice that 28 kilonewtons actually probably exceeds the rated strength of any of our equipment. So you can imagine that a fall like this at least has the potential to be quite bad. And again, we're doing this here in a scenario where we've got a stretchy rope. So this at least has the potential to be quite bad. Now, another way I want to talk a little bit about falls is you probably heard something about what are called fall factors. A fall factor is another way of looking at forces where the math is even easier. I don't like fall factors because it doesn't actually talk about the forces that you see, so it doesn't relate it back to the gear, but it does exist out there. So I want to go back and I want to use the 3 examples that we just did using fall factors, just so you guys can see what that looks like. So in our first scenario, we had a climber, a couple of bolts. He was 3 meters above his last bolt, and he was coming up and he was 15 meters off the ground. And we did the math on this. I have to do the math again real quick. So our force equals 2 times the distance that he falls is 6 meters, plus the distance the rope stretches is another 6 meters, divided by 6 is 12 is 24, divided by 6 is 4. So we have 4 kilonewtons of force on the climber, on the belayer, and 8 kilonewtons of force on the bolt. Now, a fall factor is, again, it's just another way of expressing how bad a fall is without using any actual numbers, so it doesn't use any kilonewtons. And what a fall factor looks at is so a fall factor is equal to the distance that you fall divided by the distance of the rope. So in this case, your fall factor is the distance that you fall is 6, the distance of your rope is 18, so your fall factor is 0.333. So it's not uncommon to read in magazines or in, say, things like Accidents in North American Mountaineering, will say, oh, they had a fall factor of 0.3. And a fall factor of 0.3 isn't too bad. So again, and that relates to, it's the same thing as looking at our force numbers. So we said a 4 kilonewton fall isn't too bad, and that's true. Neither a 4 kilonewton fall or a 0.333 fall factor are all that bad. Okay, so let's look at the second scenario that we had with fall factors. And in the second scenario, we had the climber, the belayer, the wall, and this distance was 9 meters to the bolt, and then another 9 meters. So our fall factor here is the same thing as it was last time. So it's the distance that you fall. So in this case, if I've got 9 meters of rope out while lead climbing, fall down, it's going to be equal to 18 divided by the total distance of rope, which is 18. So our fall factor here is equal to 1. So any fall, basically, where you have the same distance from the ground to your pro as you are above your pro, is going to have a fall factor of 1. So that's a pretty bad fall. But we also looked at another scenario where our climber was falling right onto the anchor, and they had 3 meters of rope. So this is the worst fall that you can have within this whole system. So our fall factor, in this case, they're going to fall, because they're going to fall below the anchor here, is going to be equal to 6, divided by the distance of our rope is 3, which gives me a fall factor of 2. So the worst fall factor that you can have is 2. Now again, remember that we did the math on this situation, and we said that the force on our climber, the peak force on our climber, was 14 kilonewtons, which is a lot. But there's some other ways that this actually will vary. And one of the easy ways for this to vary is by using different kinds of ropes. So let's go back to our original formula, our original math problem here, where we had a couple of bolts in between, and then we had 3 meters and then 15 meters to the ground. And so let's use a different kind of rope this time. So this time, let's use an even stretchier rope. So let's use one of those thin ropes, maybe a half rope that we use. So something, like ropes that are, say, around about 8 to about 8.5 millimeters tend to stretch about 40% instead of the 33% that we've been using. So does that make a difference? Yeah, it does make a little bit of a difference. So here, our force is equal to 2 times the distance that you fall, which is going to be 6, times the distance that the rope stretches. So here, again, I have 18, but now it's going to be 40% of 18. So that is 3.6 is 7.2. Divided by 7.2. So 6, sorry, this is a plus, my apologies. So 6 plus 7.2 is 13.2 times 2 is 26.4 divided by 7.2, and that is going to be approximately equal to 3.5. So by using a stretchier rope, we've taken the force down on our climber from 4 to 3.5, on our belayer from 4 to 3.5, and on our bolt from 8 to 7. So we've reduced it by 1 kilonewton. So that's pretty good. So what if we go the other direction? What if we're climbing on a gym rope, a semi-static rope? So I said that they have a stretch of about 12%. I'm going to use 10% just to kind of do the ease of math in my head. So let's jump back into our formulas here. Force equal to 2 times the distance that you fall, which is 6, plus the distance that the rope stretches. Okay, so here we have 18 meters, and I said it's about 12%. So about 12% of 18 is going to be 2. Divided by the distance that the rope stretches, here again is 2. So 6 plus 2 is 8 times 2 is 16. Divided by 2 is equal to 8 kilonewtons. So all of a sudden, by using a different kind of climbing rope, we have one scenario where the force on our climber was 3.5. That's when we had a really stretchy rope. We have one where the force on our climber is 4 kilonewtons. That's when we have kind of a normal rope. And now we've got a scenario where we're using what's called a semi-static rope, so a rope that doesn't stretch a whole lot, and we've managed to double the force on our climber. So we double the force on the climber, you double the force on the belayer, and now you also multiply by 4 the force on your bolt. So now we're up to 16 kilonewtons of force here on our bolt, where we were at 8. So this is looking a little bit more grim. So, and the thing that I want to point out is all we've done here is we've changed kinds of ropes. We haven't changed any of the distances. So our fall factor is the same. So in this scenario, our fall factor was 0.333, and it's still 0.333. But you can see that the forces are very different. So this is why I don't really like fall factors that much, and I would much rather talk about the actual force within the situation. So the take home here is that most of the time it's better when you're outdoors and when you're climbing to use a stretchier rope. The other really common scenario that I want to talk about, and this is where we actually get into some really dangerous situations, is when somebody is climbing and they're at an anchor and they clip in with a daisy chain. So a daisy chain is a piece of equipment, it's a sling basically, that has a bunch of little loops so you can keep it tight on the anchor. And the idea is that you always stay tight under daisy chain because a daisy chain doesn't stretch. So let's say it's about 1%. So in this scenario, what sometimes happens is you'll have an anchor and you've got your climber dangling from their daisy chain, and let's say that your daisy chain is 1 meter long, and they'll look up here, and maybe here at the top of the anchor they realize, oh crap, I forgot to tighten my, or I forgot to close the lock on the locking carabiner there. So what they'll do is they'll climb up just a little bit, and they'll go to clip that shut, and then they fall. So maybe they're not even way above it, but they'll fall from the anchor back down. So this is actually a really bad scenario. Let's do the math on it. So what's happening here, so we're going to say they're going to climb up to the anchor and then fall back down. So that distance is going to be, if they're hanging below, so our force equals 2 times the distance that they fall. So in this case, they fall 1 meter, plus the difference that this stretches. And remember, I said that a daisy chain stretches very, very, very little. So it's going to be about 1%, so it's going to be 0.001 divided by this, 0.001. So what this is basically 1 times 2 is 2, which equals 2 divided by 0.001. Once you add that in, that's going to equal to 2,000 kilonewtons. That's a bit of a bummer. So this will obviously break everything. So this is where some of this can get really dangerous. So understand that when you clip into an anchor with a static sling, that you have to stand tight on that sling. Otherwise, you might break. Well, certainly you'll blow everything up at these sorts of numbers. So at the end of this lesson, what do I want you to take away from? So I want you to first be able to identify the formula for force. So a basic formula for a static situation, force equals mass times acceleration, which is equal to, again, approximately 100 kilograms for most of us times 10 meters per second squared. So normally, if we're just dangling from a rope, we have approximately 1 kilonewton in force on us. Next thing I want you to understand is that this is very different for a dynamic situation. So you can remember that formula. Our force equals 2 times the distance that you fall plus the distance of stretch, all divided by the distance of stretch. And in most climbing scenarios with a stretchy rope, this works out pretty well. We don't get anywhere near the breaking strengths of our climbing equipment. So we did a couple of different scenarios. We came out to somewhere around 4 kilonewtons of force on our climber. Again, another 4 kilonewtons of force on our belayer, and about 8 kilonewtons of force on our, what is probably a single clipped bolt or our single piece of protection. And if those are rated at 22 kilonewtons, so we came up with a number that's about 8 kilonewtons, which is a good rough number, with and then these things have a breaking strength of approximately 22 kilonewtons. So we're staying well under the actual force of these, and that's good to know. It's nice to know that we're only using about a third of the total capacity, or at least the rated capacity of the equipment that we're using. However, once we got into some bigger fall situations, so a situation where we had an equal distance from the anchor, so remember this was a scenario where we had an 18-meter fall where the climber was 9 meters above the pro that was in the middle. That was worse. And we were getting to, I think it was 14 kilonewtons was the force on our bolt. So now we're getting up to using about half of the capability, and then we actually exceeded the capability of our bolt when we had a factor 2 fall. So a fall where they fell a long ways, but they fell right on the anchor. So that is really what I want you guys to take away. And then the third thing I want you guys to take away is that different kinds of ropes have different stretch amounts, and the stretchier rope, the lower the force is in the system. So if you're ever trying to figure out how to minimize the amount of force, what you want to do is use the stretchiest rope possible, and then be especially careful anytime that you're using static ropes. So anytime that you're using slings or daisy chains or static ropes when you're doing things like canyoneering or abseiling, because those are when you can get into some really scary numbers, hundreds or even thousands of kilonewtons, and the system would fail long before you actually approached those sorts of things. So thank you very much. I hope you guys have a good evening, and if you have any questions, just let me know.